Hi, everyone. Yeah, thank you for coming here today, and also those on Teams. And also thank you, Luis and the Energy Futures Lab for inviting me to give this talk today. So I am Lívia Cupertino Malheiros. I'm a lecturer in Mechanics of Materials in the Materials section of the Department of Civil and Environmental Engineering. I'm also a Marie Curie Energy for Future Fellow, which is a co-found program also managed by the Energy Futures Lab with the European Union and also the company Iberdrola. So the talk of today, it's about metallurgy for hydrogen infrastructure, which is my main field of research since my master degree. And today I would like to present to you some studies I have been doing related then to hydrogen embrittlement, which is one of the major challenges when we talk about hydrogen infrastructure. So before I actually start my talk, as an early career researcher, I'm building my research group. So here is an overview of the group I'm building. And today I'll talk about hydrogen embrittlement, as I said, but I'm also starting research in other fields, such as corrosion for offshore wind, oxidation, and plasticity. And those are the people that are starting this group with me, and some of them are also in this room. So as I said, my talk will focus on hydrogen embrittlement. And before I move to the actual research, I would like to explain to you why hydrogen embrittlement is a big problem. So hydrogen embrittlement is not a new problem, it's a quite old problem and has been a challenge along many decades across multiple industrial sectors. And here I'm showing some examples with those images on the early days of steel making, when they couldn't remove that much hydrogen inside the liquid steel, and when it casted, hydrogen gas was inside, causing cracking. We had lots of problems for decades on the energy sector, especially for offshore structures, as you can see here on the failure of this platform, and also you can see wind energy. There are problems associated with nuclear industry, with the formation of hydrides in zirconium alloy and cracking on nuclear reactors. There are also problems associated with automotive industry, here illustrated with a cracking in a galvanized steel. So when you do coating, hydrogen can enter, and in aerospace and so on. So it's a very challenge that impacts lots of sectors in society. Okay, but what is this challenge? Specifically, when we are talking about hydrogen embrittlement, there are 3 steps involved. So the first one is hydrogen absorption. Sometimes it's neglected by the mechanical and material engineering community, but if the alloy making people have done a good job and it didn't start with hydrogen on your alloys, for hydrogen embrittlement actually to take place, hydrogen needs first to enter alloys, because hydrogen embrittlement is a problem when hydrogen is in the bulk of alloys. Okay, so this is the first step, hydrogen absorption, and hydrogen can enter here a metal surface when alloy surface, so the metal surface, is exposed either to aqueous electrolytes, and that can be even like atmosphere, because you have water vapor, or gaseous environment, so H2 gas, that is more relevant when we are talking about hydrogen gas as a green energy. Okay, once hydrogen is inside, is in the bulk of the material, the second step is the hydrogen moving inside of the material, of the metals. And hydrogen will move relatively fast, even at room temperature, which is called diffusion phenomenon. And specifically, hydrogen will also interact with the structure of alloys. So whichever type of defect of this crystal structure, the structure of alloys that have positions where hydrogen can be more stable. So it tends to accumulate in those areas, and this phenomenon is called trapping. So a third step, and actually is the one that has more engineering relevance, is how this phenomenon, so hydrogen moving inside of the alloys, interacting with the structure, at the end will actually cause fracture. failure. And that's what we are talking about when we talk about hydrogen embrittlement. It's like hydrogen moving, get absorbed, moving inside of the alloys, and resulting in cracking, in failure of the structures. Okay, but how serious is this? So is hydrogen really modifying that much the fracture behavior of alloys? And the answer is yes. And you can see here in these two graphs, the first one here is a stress strain curve. And if you have never seen that before, it's basically a test where you take a bar or a plate and you pull it. And what you are showing here is the force is proportional to force and elongation. So this is four tests done for the same steel material. And the only difference here is that for some of these tests, the sample was tested in air and for others with hydrogen. So what you can see here is that testing it in air, you get this type of elongation, which is related to the resistance to fracture. But by doing the same test with the same material with increasing pressures of hydrogen, you get a decrease and a dramatically decrease of the elongation that the material can withstand. So here, half of the elongation. So it's even more clear when you plot here, you do fracture resistance tests. And what's plotted in this middle graph, it's fracture toughness that's proportional to the energy necessary to fracture a material. In here is plot this fracture toughness as a function of hydrogen pressure. Again, the same material, this is a pipeline steel, low strength pipeline steel that can be in our grade, our gas natural grade, being a test. And here, the highest value of fracture toughness indicates that the material is difficult to break. You need to provide lots of energy. And lower values, it breaks easily, which we call brittle. And here you can see how much hydrogen gas pressure reduce this fracture toughness. And this is not only, not even the worst example. One thing is if we go now for higher strength steels, and this is interesting for us because if you go for high strength steels, for the same application, if you have some load bearing capacity that the structure can resist, now you can use smaller sections and use less steel, which is more sustainable. And if you do go now for higher strength steels, now what you can see here is for a same environment on the graph in the middle, for a same environment, now this decrease of fracture toughness is proportional to the strength of the steel. And it gets so bad that for very high strength steels, you get values of fracture toughness that approach ceramic materials. So you want to design your structure with metals that are ductile, that can resist more deformation before fracture, and you can end up, depends on the environment, with a material that's very brittle like a ceramic and can crack very easily and can result in a catastrophic failure. So it's a very big problem. And as I said, I hope now you're convinced it is a big problem and it's a challenge for multiple industrial sectors. And more recently, it has been seen like more and more people are interested on hydrogen embrittlement because there are lots of government and in the sector interest on decarbonizing, of course, our energy. And hydrogen is one of the key players that can help us to decarbonize society. And this hydrogen embrittlement could now then compromise our ability to provide safe and also cost-effective hydrogen transportation and storage infrastructure. So you can see here some articles in the news saying how we want to by now already start transporting hydrogen in our current pipeline grid, and how so you have that project in Europe where 42 natural gas operators came together to try to use the current natural gas pipeline grid for hydrogen. And a catastrophic here example of an early structure for hydrogen that has exploded and something that we also want to avoid. So I really hope by now you understood that hydrogen embrittlement is a problem and also is something that can compromise the transition to a green hydrogen economy. And So with that introduction in mind, I would like to come back to the 3 steps related to hydrogen embrittlement. And now I will go in each of them, providing you some research results related to these 3 steps, starting with the first one, that's hydrogen absorption. All right, so the first thing you do need to understand is that the extent of hydrogen embrittlement, so how severe it is strongly linked to the hydrogen concentration absorbed inside of metals. So that means that if you want really to have a fully prediction of hydrogen embrittlement for a given application, someone needs to be able to predict how much hydrogen enters inside the alloy when exposed to that environment. And that has been the topic of my earlier research, how we can make this prediction. All right, we have then 2 environments. So to be able to do a fully prediction of hydrogen embrittlement, then for a given metal surface exposed to an aqueous electrolyte, we should be able to predict how much hydrogen enters inside the alloy based only on known bulk parameters of this electrolyte. They usually pH and potential. All right, we should also be able to predict for the hydrogen economy how much hydrogen enters, get absorbed in an environment if it is exposed to a hydrogen gas pressure. And because those involve similar and related physical chemistry, we could also establish equivalence between those. So this is a vision of this research on hydrogen absorption. I have not get there yet, but I'll show to you some results. And those results concern when metal alloys are exposed to aqueous electrolytes. All right, so the approach I decided to use, it's called reaction rate approach. So first, you need to identify what are the main reactions, electrochemical reactions that happens at the metal surface when exposed to an aqueous electrolyte. So hydrogen comes here from electrochemical reaction, a reduction of either water or a proton. Then you have lots of hydrogen that will be adsorbed here at the metal surface. A great part of this hydrogen will just desorb either chemically or electrochemically, and a small part will enter the metal. That's the part that we call absorbed and is related to hydrogen embrittlement. So once identifying those reactions, I take then the reaction rates of all those reactions that come with some constants, some kinetic constants that I'm interested to know, to be able to predict the hydrogen production and absorption. And finally, by just doing conservation of the adsorbed hydrogen and the charge, we can get on a model. But of course, this model needs some kinetic constants, and therefore I went then to the lab to do some electrochemical experiments. The 2 main questions I'd like first to know is what's the dominance mechanism? So there are 2 mechanisms possible among them, combining these 2 reactions. That's called Vollmer and Tafel, or Vollmer-Herovsky reaction. And I also would like to know, by using this approach coupled with experiments, if I could predict absorbed hydrogen concentration, and if I couldn't, know the limitations of this approach. All right, so I have done a series of electrochemical tests in the lab. Part of those tests are related to the activity of the metal surface, so how much hydrogen get produced. But in those parts here, we are not measuring the one that has get absorbed. While another part of the experiments, they use this approach that's called electrochemical permeation, in which there are 2 electrochemical cells. So one cell, it gets, again, hydrogen produced at the metal surface, but now we can detect in the other side the hydrogen that got absorbed at the membrane. In this case, I use 2 model materials, iron, pure iron, and nickel anode. All right, so overall, by doing experiments related to the metal surface activity, I could incorporate quite easily the effect of pH on the kinetics of hydrogen production, and also see that the dominant mechanism was Vollmer-Herovsky for all the conditions tested, so a wide range of potential and pH. And when it gets then for the hydrogen absorption, the first thing I have done then is taking the data of permeation. And with the data of permeation, we can get, using those equations in that side, a relationship between the pressure of hydrogen, the equivalence between the two charging methods. So one, the pressure of hydrogen, here illustrated by F fugacity, and the electrochemical charging, here illustrated by a potential. And this was actually an approach using this permeation measurements to get two constants to be able to do this equivalence between those two mediums. And what the work, but this work has shown when I plotted the data of my work and from previous works, is that there are some limitations on getting equivalent fugacity from this approach. And there are quite a lot of dispersion. So it's difficult to establish this relationship. Finally, I tried then with the data acquired and that approach that I said in the beginning, the reaction rate approach, to get how much hydrogen get absorbed. And then by fitting my data and data from the literature, we can satisfactorily predict this data, that is the current density associated with hydrogen production, potential, and pH. But then when it gets to really predict how much hydrogen get absorbed, what we see with this model is that we tend, here is in this y-axis, the absorbed hydrogen at the surface. So one indicates that the surface is fully saturated with hydrogen. And what we see with this approach is that it tends to give to us the model a completely saturated surface quite quickly. And that completely overestimate how much hydrogen actually gets inside the metal and the dependence with over potential. So this is something that I'm still working on. And it seems here that there are some limitations or like some physics missing on the modeling or either, and maybe both, some also limitations of the experimental method. So this is ongoing work, and it's work that my postdoc UAA has been working now 1 year, continuing this research. And yeah, it's something that I will pursue. But, and our over, like this is just to illustrate what's really the aim. So here it's providing some maps of the equivalent fugacity. So you can get basically for the predictions of hydrogen absorption. In that case, the metal is exposed to an electrolyte in terms of potential and pH, and also an equivalent hydrogen absorption when the metal is exposed to the pressure of hydrogen. Okay, so this is what I'd like to say in this first part of hydrogen absorption quite quickly. And now I want us to assume that hydrogen is already inside of the steel, and we are going to look at the bulk. Okay, so the second thing, as I said, is once hydrogen is already in the bulk, and hydrogen will move inside of our metal structure. And if you are not familiar with material science and alloys, what happens, they are crystalline, so they have very ordered the atoms are very ordered, and hydrogen is the smallest atom, so it can move quite easily on the E-space, called interstitial spaces, between the metal atoms, okay? And this hydrogen that will be moving through these interstitial spaces is what we call here lattice hydrogen or interstitial hydrogen. All right, hydrogen, when it's moving in this metallic structure, this metallic structure is not completely well ordered. There are some defects. So it's basically where the atoms are not very well ordered and there is some space over there. And then on those spaces, hydrogen will tend to be attracted to them. So if you think on an energy, here in y-axis is energy, and x is the diffusion path of hydrogen. So when hydrogen is here in the beginning at the interstitial site, there is a very small energy barrier. But also when hydrogen is in this interstitial site, has smaller energy, but not that much smaller. But there are some spaces that the structure is not very well ordered, where hydrogen gets has much lower, I don't know if this point is working, but much lower energy. And when hydrogen is there, enters there, it's more difficult for it to leave. And that population of hydrogen we called trapped hydrogen. All right, and this trapped hydrogen has actually been seen nowadays, can be seen using atom probe tomography. And here there is a research that's not from mine, but from the literature, where you can see hydrogen accumulated there at a grain boundary, a type of defect. All right. So my researching, one of the research I have done related to the diffusion and trapping considers high strength, low alloy steel. So as I said, high strength steels are very, can be very susceptible to hydrogen embrittlement. And in this research, I was comparing 10 grades of steels. These high strength steels, in this case, they have, it's one type of steel that has a structure that's called tapering martensitic structure. So what you can see in this graph first is the strength of those alloys, the y-axis, and here in the x-axis is the tempering temperature, is just the temperature of the last treatment before selling those steels. So the tempering temperature or the yield strength on these steels are mostly related to the tempering temperature and the composition. So those steels there, they are in red, they have the same composition, and then the strength is mostly related to the tempering temperature, while when you heat it up more, it has lower strength. But then you can also control the strength by changing the composition, and this is doing by adding some elements like chromium, molybdenum, and that way you get similar level of strengths for different tempering temperatures. And this is good because if you heat it up more, you can annihilate some defects. So this work we first compare what you get in terms of hydrogen diffusion and trapping behavior for all of those steels. And what I actually did is some experiments that characterize the structure of these steels and link with the hydrogen behavior. So basically how fast it diffuses inside of those steels, they moves inside of those steels. Okay, so the structure of these steels look like more or less like that. And what we are interested in here is in the defects of these structures, these trap sites where hydrogen can get accumulated and maybe eventually cause fracture. So in these colorful diagrams, what is showing is called grains. So the metals have lots of crystals with different orientations, and each of these colors is one orientation. Here, what you can see are dislocations. So you can see these lots of black lines, and in these steels, they have lots of them, and it's because they are quite strong. And those you can see lots of particles. Those are carbides, the second phase particles, where hydrogen can also accumulate. All right, so the first part of this research, I used this experiment, again, permeation. I talked about it before. And in this case, what I obtained with this experiment is the diffusion coefficient. So how fast is just a measurement of the speed of hydrogen moving inside of these metals. And here is plotted as a function of the strength of those steels. And you can see that the stronger those steels, the smallest, the slower the diffusion kinetics. So basically, the structure features that are hardening these steels are also trapping hydrogen with a small flexibility in the design, but the correlation is quite strong. All right, and it's what I have just said. And then one thing to notice is that this diffusion here, this hydrogen diffusion kinetics here, incorporate the two phenomena I said earlier. So the diffusion coefficient at the lattice, that's DL here in pink, and also the trapping effect. And this trapping effect, this attraction to hydrogen, to these structure features, basically depend on two parameters. One is how many of these structure features there is in your structure. That's usually called NT, that number density of trapping sites. And the second one is how strong hydrogen is attracted to these features. That is the energy of attraction, is a binding energy. So for this research specifically, I have seen that for these steels is not really the energy, how strong the steels or the hydrogen is attracted to the defects, the trapping sites that changes and justify the differences on hydrogen diffusion kinetics, but is the number of these trapping sites. And here you can see a correlation between the diffusion kinetics of all these 10 steels with the number of the trapping sites. And among all these steels, the one that has a little bit more of vanadium was the one with the slower hydrogen diffusion kinetics, and that could be associated with a population of few nanometers inside vanadium carbides that was identified for this steel using synchrotron XRD and transmission microscope that can strongly interact with hydrogen and trap hydrogen. All right, so this is the part that I want to show to you some research on hydrogen actually moving inside these steels. And I wanted to move to show to you 2 examples of research for the third part, that is hydrogen-assisted fracture, and is actually the one that has lots of engineering relevance. So now we know that hydrogen enters steels, hydrogen is the bulk, in the bulk, hydrogen is moving, hydrogen interacts with the crystal defects, but now we want to know, but why this results to fracture? And if when it does, can we predict that? And that is actually very relevant to us, either to design better performing alloys, but also to be able to predict hydrogen and establish better testing methodologies. Okay, so in this first work, I designed these 2 experimental methodologies to be able to test the effect, separate the effect of trapped hydrogen only on the fracture and the hydrogen flux on the fracture. So starting with the first one, what I have done is pre-charge some steel samples, now samples that are tensile specimens that I can later on do the tensile test that I showed in the beginning, and let it to the hydrogen to disturb in air. So let it in basically on the desk, leave the hydrogen that is the lattice hydrogen to disturb, and I just want to evaluate if trapped hydrogen, what is the contribution to fracture of the trapped hydrogen. Okay, the second test, then I put now the electrochemical permeation on a tensile testing machine. So in this test, we have a condition now when we will test the sample, like pull the sample, will be a condition where we have a constant flux of hydrogen inside of the samples, because here there is a charging cell and here detection cell. And this condition simulates more or less if you have a pipe, hydrogen being charged in the inside, and the disruption of hydrogen from the outside or the outer diameter of the pipe. So you have a gradient through the thickness and a flux of hydrogen through the pipe. All right, so the first results I'm showing to you, again, tensile curves. Here they were done for different notches. So you have on the top unnotched and on the bottom notched specimens. And here what we can see is that both caused embrittlement, so the decrease of the elongation, with the hydrogen flux are the blue curves causing more embrittlement. Okay, the second part, I was trying then to understand that. When we look first, when only trapped hydrogen is present. So the first thing I do then is look at the fracture surface, what tells us on the microscope. So in that case, we can see that the morphology of the fracture surface is full of these voids, which is the characteristic fracture of morphology of those steels when fracturing air. That's a ductile morphology. Okay, and the second thing, I have done a cross-section that I have then come to image those voids, so those damage around particles on this cross-section here. That is the second figure. And then couple those experimental results with some finite element elastoplastic simulations. What I could see is that hydrogen reduced the critical stress for the decohesion around those particles. And that can justify why trapped hydrogen causes certain level of embrittlement, even though the fracture surface, the fracture mode didn't change, remained ductile. Okay, but now looking on the test on the hydrogen flux, so now when you look at the fracture surface, you already see it completely changed. It's nothing like the one with the voids. And this morphology is called quasi-cleavage. It illustrates that it's more brittle. And now again, I couple it with finite element calculations, now consider elastoplasty, but also diffusion and trapping. And here I was interested. So you can see here overview of the fracture surface. In the side where hydrogen is entering, we do have this quasi-cleavage fracture. And then in the other side, you just have a ductile, like the cracking propagation the ductile way. And what I was looking with this model is establishing the necessary hydrostatic stress, plastic strain, local concentration flux necessary to fracture. So when you do this test, you basically get macro parameters, stress, strain, concentration, but coupling with finite element method, then you can get local ones that are actually a local condition for fracture with hydrogen. I also try to link this quasi-cleavage fracture that you saw with hydrogen flux with the structure of those steels. And what I noticed is we didn't have this type of fracture that are fractures where you see grains at the surface that indicates that the fracture is intergranular. We have this fracture morphology. But when I compare with the structure of those steels, those martensitic steels, they have, in addition to those boundaries, lots of inner boundaries. And I can see that the fracture surface resembles very much the structure of those steels. So this is an indication that the fracture is happening at the inner boundaries. So another indication I saw is that basically the size of the quasi-cleavage features related to the size of the microstructure, with larger microstructure having larger quasi-cleavage features. And finally, I did EBSD at the fracture surface, and I saw that the fracture happens mostly parallel to the 101 planar family, which is also the interface between some of these inner boundaries of martensite. So all of that indicates that these inner interfaces are cracking with hydrogen. And another feature that I also see that was often related with the hydrogen embrittlement were some undissolved big carbonitrides that can come with the process and should avoid those. Okay, so now finishing up this example, I will then quickly show to you another example is still in this topic 3 of hydrogen-assisted fracture. And again, coupling experiments with modeling to try to get more information, in this case, to test and predict hydrogen-assisted cracking. So in this final example, what I would like then to understand is, again, hydrogen embrittlement, hydrogen-assisted cracking, again of high-strength steels, but now when they are exposed to very corrosive environments with a gas that's H2S. So the importance of this also for the energy sector, it can be for oil and gas, but also geothermal. And this gas, it favors the absorption of hydrogen inside alloys. So when this gas is there, much more hydrogen enters. And as you know, hydrogen embrittlement is related to the amount of hydrogen. So now you get much more hydrogen embrittlement. All right. So to do that, I come back again for my hydrogen permeation. But now in this side, the charging side, we have solutions with acid solutions with H2S. And here in the exit side, I am again detecting hydrogen that has been absorbed into my here steel membrane. So what you can see here is this flux or this current density that is proportional to hydrogen that get absorbed in the steel over time, and here during 30 days. And this was done for hydrogen H2S, so H2S pressures from 3 to 100, and as I said, H2S favor hydrogen absorption. That's why for the red curve, you get higher values of hydrogen absorption here in the beginning. Another thing you notice here is that over time, this hydrogen absorption tends to decrease. And it decreases because now hydrogen is entering the steel because of a corrosion process. And as the surface evolves, and in those cases here with 10 and 100% H2S, there is a formation of a corrosion product layer that will slow down the corrosion kinetics and then slow down the hydrogen absorption. And the benefit of doing these experiments is that now, when I'm doing my modeling, I can use G as a boundary condition and take into account those effects, the effect of the pressure of H2S, and also the effect of the corrosion product on my simulations. Another thing that those permeation experiments give to us is the diffusion coefficient of hydrogen in those materials that's necessary also when we are doing diffusion modeling. All right, so here it was developed then a new geometry of a compact scent test. So it's a fracture test. Here, this test was then performed in those cells, which there is an acid environment with H2S. In those cells is a constant load during 30 days. And basically what we get is if it pass or not pass. And here it's very pass means the sample didn't crack and didn't pass the sample crack in just 30 days. And that was done with different loads applied in those samples that have a pre-crack. In the samples that cracked, we can see again the same sort of fracture morphology that's quasi-cleavage, but here with corrosion products on it. All right, so this is the experimental test, but then we also do the same numerical test to see if we actually get the same thing. So for the numerical test, again, the same geometry that here can be modeled by half of this plate in 2D. And here it's applied a couple deformation, diffusion, fracture model. So we capture all the physics involved, and now we do the same test, but numerical test. And those are the results of this test. So the way you can interpret here, it's the time to failure. So those samples that are on times before here 200 hours have failed. The ones over there, they didn't fail. And this K1 is related to the force that has been applied. And very important here, we can determine the threshold value. So the necessary value, the value necessary to fracture those samples. So above then all those samples fracture, below it no samples fracture. And we got a very good correlation between our experiments and the numerical modeling. So this is actually the final result that I want to show to you today. And just to finish up, I'll just show two other research of current PhDs that are performing the lab. So it's ongoing research. So here, finally, just to illustrate again, oh, sorry, I'm not sure if I can play those two at the same time. No, I can't. Okay. Let me see. This is just a test that I like also to, okay, it doesn't want to. Anyway, so this is just tests that I usually play at the same time for you to see how much a material fracture much quicker with hydrogen, but for some reason it doesn't want to play there. But anyway, this is a research of an ongoing student of mine that's actually over there. So he is working on my more fundamental research so far using nickel for us to try to understand better the intergranular behavior of nickel and try to understand what are the boundaries, those defects that are most susceptible. And he has just finished up his first set of results here identifying which grain boundaries, so these defects are most susceptible to cracking, and then he can move on to alloys, other nickel alloys of more engineering relevance, for example, for aerospace. Another ongoing research of a student of mine, we are now looking at the welds of pipelines for the current gas grid. So pipelines from different ages, some more modern from the 90s, some vintage from the 70s. And those welds in those pipelines are the weakest link for fracture. So as part of the work, as there is an interest to repurpose this natural gas grid for hydrogen, and there is an interest for economical reasons that we can put high pressure hydrogen in the network, we are then studying, investigating those welds to understand better the hydrogen diffusion trapping behavior inside them, and also in partnership with Paris testing then on high pressures of hydrogen, the different parts of the welds that has this beautiful microstructure that can be quite challenging sometimes. So that's all from my side. Thank you very much for listening, and I'll be happy to answer any questions you might have. Thank you.
Last one. So for the hydrogen absorption, so I guess both hydrogen ions and also hydrogen molecules, they can both get into the material. Is that right?
No, not really. So yeah, I went quite fast, but I think if I go back on the scheme, will be, yeah, maybe even the first one. So if what enters the steel is actually the hydrogen atom or the alloy. So in the case of a gaseous environment, that involves the dissociation of the H2 gas into the metal surface. And then these atoms are first adsorbed at the metal surface. And then part of these adsorbed metals at the surface get absorbed inside. And the other part will just dissociate and go back. So it's the hydrogen atom. In the electrolyte, the same thing is always the hydrogen atom. In that case, hydrogen comes due to the reduction of either a proton or water in the electrolyte. And then you get these sorts of the reactions. But again, you have this adsorbed hydrogen atom at the surface, and part of it can enter the surface and get absorbed, so diffuse through the interstitial sites. So in both cases, in any case, is the hydrogen atom that can move inside of the metal.
Okay. So is that positively charged? I mean, the atom is kind of.
I mean, you are in a metallic bond. So when hydrogen atoms inside, as all the other atoms of metals, they tend to donate the electron to the electron cloud, and you could think it more or less like a proton moving around, but it's the hydrogen atom. When it leaves, it's the hydrogen atom at the surface, and then it will interact with the crystal structure of metals. Yeah. As the other metals around, yes.
Yeah. So basically, for all of the theoretical or the physics parts,
yeah,
also take and hydrogen atoms into account, right?
Yeah. So, for example, if you are going to do some DFT simulations, So if you are doing some DFT simulations, for example, you are taking into account this hydrogen into your metal structure and the disturbance that it can cause. So it can be, as you said, can be electrical fields, can also be elastic fields, but hydrogen is quite small. So the elastic sometimes not that big, like the deformation of the crystal is more the electric part. But yeah, they took it into account. So if you are going, for example, here are some simulations to see where hydrogen, which interstitial site, so which of this space is more favorable for hydrogen, for example, and then it's based on the energy, the disturbance of your crystal structure when you have a hydrogen atom inside. I don't know if that answers your question.
Yeah, thank you. May I ask another one?
Yeah.
So when you do the embrittlement experiments, two, right? One is with a kind of fixed amount of hydrogen, another one with hydrogen flux, right? Which is that a kind of continuous hydrogen absorption during your tensile testing?
Yeah. So in the flux one, So in the other one, no, because it was pre-charged, so it was not in the environment when I test. This type of test here, and also the later one, when the metal is still in contact with the environment, so hydrogen is still in. So in this test specifically, I first did the pre-measure. So I let the flux, so the hydrogen flux being stable first, and then I do the sample. So then the tensile test initiated. So after there was already a stable flux of hydrogen inside. So in all those tests, so there are two basically big methodologies. So one, you pre-charge your sample and then you do the test. The other one, you do the test inside of the environment. That it's basically, I think it reproduces better. depends on your application, of course. But for some applications, it will reproduce better the conditions in the field. And then in that case, hydrogen is entering while the test is being performed. And of course, that will also change the absorption. So once you have a crack, you have stress fields. So here we discuss about trapping, but hydrogen also accumulates at stress fields. So yeah, so you also tend to accumulate more hydrogen once you have a crack, a defect.
Yeah. Actually, would that be possible to take this kind of accumulation, or you get more and more hydrogen into the material into account in your modeling?
Yeah, it does. When we not here is quite static modeling, but this type of modeling here, it does take into account.
Okay.
So it's a model that there is the first diffusion fracture phase field model. So when the crack is evolving, it's taking into account already the change on the stress field, and you also hear the diffusion of hydrogen, and then it's good because then you can capture the kinetics. So in those cases, you have in situ experiments. There are lots of kinetics involved. So you have the kinetics of how fast hydrogen moves. You have the kinetics of your cracking propagating, and those will related with each other. So those type of model, yes, that can capture all of this. And actually, when we do it, for example, we can see in our models the same thing. So see, when the samples break, it breaks very quick. And when it passes here 2 days, for example, they will not break anymore. So these things we can understand when you look at the kinetics of this phenomenon. Yeah.
Sure.
Some questions online. Someone's asked, how much time does it take for hydrogen desorption to begin in BCC stills after ex-situ hydrogen charging?
It depends on your geometry. So basically, you can estimate that. Just take the diffusion coefficient of your material. So for a BCC still is more or less 10 minus 10 meters square seconds. And then you take your geometry, and then you can consider if you put in a hydrogen environment enough time, you can consider a situation where you start with fully saturated. And then you just need to solve Fick's law with the boundary conditions that apply. So it would depend. It would depend a lot on your samples. For those samples we have done, usually you do some finite element simulations with Fick's law, then you know the time, and then you just leave that time. So for the samples is what was done. For BCC, it's diffused relatively fast. If you have some samples like lab samples, in few days, it's fine, like it would diffuse completely. So you can do the simulations just to verify. But BCC stills, it diffuse out quite quickly, which for this test was good because I only want to test trapped hydrogen. But if you want to test your whole hydrogen, pre-charged tests for BCC stills might not be a good option. You need in situ tests, just because a great part of hydrogen can leave your sample before you start the test. So more realistic tests will be in situ.
Well, someone's asked, is it only vanadium carbides that reduces susceptibility towards hydrogen embrittlement?
Yeah, one thing I need to point out here that could be misleading. The vanadium carbides here did reduce the kinetics of hydrogen diffusion. I didn't say it reduced hydrogen embrittlement susceptibility. And in that case, when you test those stills in situ with hydrogen entering, you could saturate these traps. This didn't result in a better hydrogen embrittlement susceptibility. So this is the first point I want to say. The second point, no, it's not only vanadium carbides, and any structure feature that trap hydrogen. And now you need to look at how many you have in a structure, what's the binding energy. But in principle, lots of other second phase particles and also lots of other types of crystal defects can slow down diffuse kinetics. The question is, can they prevent hydrogen embrittlement? And that's a much more difficult one. Yeah.
And was asked, can coating help to avoid hydrogen absorption? And then a follow-up to that is, and can we coat pipelines against hydrogen embrittlement to repurpose them?
Yes, I mean, they can prevent hydrogen absorption if you put a coating in which hydrogen doesn't absorb, hydrogen cannot enter, then hydrogen would not enter your metal. I mean, the problem we do have with coating, and I think something that we all consider a bit dangerous is that coatings can, and usually they do, if you are talking about the infrastructure that will stay there for many years, they'll present defects. And as soon as, if you have a coat here, as soon as there is a defect, you are exposing your weak bulk material. If your material is not residential hydrogen embrittlement, it can also be quite dangerous to only rely on coating. So in my personal opinion is that you can use coating, but you should also aim for a material that has a good resistance to hydrogen embrittlement.
Okay, thanks for the interesting talk. I just slide 29. It's about your number density of the trapping size. How do you measure it?
Yeah, it's probably. Yes. So this was also with permeation, with electrochemical permeation. So I didn't put the equation here. So it's an estimation of.
So estimation, not measure.
It's an estimation of the density of trapping sites using also permeation experiments. Yes.
Okay, thank you. Thank you.
Some more online ones if there are none in the room. Someone's asked, how do you carry out measurements of diffusion and hydrogen concentration in the specific case of welded structures? So are the welds large enough to extract microspecimens, or have you developed a local method for measuring hydrogen concentration?
No, there is no local. I mean, I'm not working with methods. So the way we are currently doing is going for smaller samples, both for mechanical testing and for hydrogen diffusion and concentration. So if I move here, yeah, so we can extract samples in different areas of the welds, characterize the microstructure, and here what's illustrated is a TDS. It's a way to measure thermal absorption spectroscopy, the hydrogen that's absorbed, and also get parameters of trapping in diffusion. So what has been done in this study is really taking samples from different areas of the wells and then doing the diffusion and trapping with permeation TDS and test with smaller scale samples. Yes, in different zones.
Quite a few online questions. Someone's asked regarding hydrogen embrittlement mechanisms and the permeation tensile machine, have you identified any dominant mechanism?
I mean, this is a question that's a lot of debatable on the literature. What we see with those tests, so basically here, when you look with what are the links in the structure, it points out that interface are breaking. So it seems that there is some sort of decohesion mechanism that is causing the fracture. It's not possible to say that's only that. So when I was establishing some local fracture criteria, so using modeling to see what are the stresses and the plastic strain necessary for fracture, it seems also that plasticity can help. So overall, for these steels and the agreement with literature, we say that we have a combined effect of plasticity and decohesion. For some cases, we see that decohesion is more evident, but yeah, it's still debatable, I would say.
Someone else has asked, in slide 11, you mentioned about establishing equivalence between electrochemical and gaseous charging. However, in both the cases, the absorption kinetics are different. In electrochemical charging, we get gradient in concentration along the thickness, whereas in gaseous, it is more of similar concentration throughout the thickness. How do we normalize them?
I'm quite not understanding where I talk, because when it's the person saying about thickness, I understand that's already talk on the bulk. Yeah, I'm not really understanding the question. I mean, the way we think here on an equivalence is that in that case of the aqueous electrolyte, the first step of it is actually producing hydrogen gas. So you're first producing hydrogen gas, and then part of this hydrogen. So you could think on equivalent pressure of hydrogen gas that will be produced in this environment. which would be equivalent to here, where you are actually exposing the metal to a hydrogen pressure. So that's what I mean by equivalence. So the equivalence in that case would be the bulk pH and potential producing a certain hydrogen pressure at the surface of the metal. That would be equivalent to that case. In a sense, the equivalent is what is the electrochemical charge parameters that would result the same absorbed concentration if my metal was exposed to a hydrogen pressure instead of an aqueous electrolyte. Yeah.
This is the room before. Okay. Someone's asked regarding the lathe hampered marking skills. The speaker mentions absorption difficulty. Does the formation of carbides M7C3 and M23C6 affect the absorption kinetics as being precipitated at grain boundaries? And how is modeling done for hydrogen absorption at the grain and atomic?
Okay, I didn't mention much this option, so I think it's talk about diffusion and trapping. If that's the case, about carbides. So those carbides are carbides that I didn't really observe for this still. There is still, even though it has chromium, I think this M23 C6 maybe it's rich in chromium. Those steels the maximum was 1% of chromium. We didn't observe that, so chromium was mostly inside of cementite. So we did, I mean, I didn't show you, but we did a whole characterization of carbides and also look at the thermodynamics, what it predict, what we will actually get. So was a big, this was actually my PhD, so it was a big part of it. The one for those, it's quite low alloy that we observed that affect more the kinetics was really, the diffusion kinetics was really vanadium carbide, which is basically vanadium titanium carbide. Yeah.
Other questions. Could a test in an electrolyte corrosive environment be quantitatively correlated to an equivalent dry hydrogen pressure in terms of embrittlement severity?
Yeah, this is the aim. So this is the same aim. When I said here that we had the aim of the equivalence, the same aim. So the aim would be in a situation with what we're cathodic and polarized, but also on a corrosive system. And a corrosive system, as I show here, we also have the challenge that the surface is evolving. I mean, there are lots of challenges. With some modeling, you can. So one of the challenges is that we say, I want the hydrogen absorption in terms of bulk pH and bulk potential. But of course, when corrosion process is taking place, the local values are changing. So there are some modeling to try to see how those are changing. This is one thing we need to incorporate. A second thing we need to incorporate is that the surface is evolving. So we would need to incorporate this corrosive film. But eventually, yes, you could establish some correlation between the corrosion kinetics and the hydrogen absorption. And if you do so, then you can get equivalence. It's possible. I have not done it, and I'm not aware anyone has achieved that yet. But I don't see why it would not be possible. Yeah.
And final question. You said the fracture surface does not appear to be fracturing down grain boundaries. Is this because the dislocation density here is preventing fracture? Is this a strategy that could be used within the bulk to increase the dislocation density to resist hydrogen embrittlement?
Well, what I said, maybe I was misleading. So what I said is that when you look at how these temporary magnetic steels were breaking, you don't think at first glance that this is related to grain boundary decohesion, because intergranular fracture, as shown also on the work of my PhD for nickel, usually has these features here that are axic grains. However, in that case, it did look like as the grain structure of a temporary magnetic steels that has lots of inner boundaries is breaking. So it's more pointing out to interfaces breaking than the influence of dislocations itself, those results, yeah.